If you've ever noticed your car's navigation system sigh when you take a wrong turn, or if you've ever raised an eyebrow at how online ads suspiciously show things you've just talked about, don't worry, you're not alone.
Welcome to AI Explored. AI Explored.
Greetings, listener, and welcome to AI Explored, the human's guide to the future. I'm your host, Jeremy, a validated human. Well, on at least a few certificates. Today, we explore the fascinating world of machine learning, or ML for those of us pretending to save time. ML is at the core of modern AI's magic. It's akin to the wizard behind the curtain. Only this wizard learns and evolves with every spell cast. From predicting your next favorite song to diagnosing diseases, ML's influence spans industries, reshaping everything from finance to healthcare and beyond. Before we start our journey today, a quick note. This episode is organized into chapters. You can jump around to explore the bits that interest you the most or digest it all in one go. Think of it as your personal tasting menu of AI knowledge. We'll cover the building blocks of machine learning, from straightforward algorithms like linear regression to intricate structures such as neural networks and decision trees. I'll help you understand what machine learning is and discuss its critical role in advancing AI technologies. But we're not stopping there. We'll explore everything from fundamental data handling techniques like data cleaning and feature engineering to advanced concepts such as backpropagation in neural networks. This is where AI gets smarter, fine-tuning its approach as it gobbles up more data and experience. And if the terms we're using seem a tad mystical, like wizard spells perhaps, loosen your grip on your towel and remember, don't panic. We'll break everything down into plain English, making sure you can talk about AI at your next dinner party without needing a PhD in technobabble. And because we can't talk about AI without considering its impact, we'll tackle the big questions around AI ethics. We'll look at how AI is shaping the world in terms of privacy, security, and fairness, and what that means for us as a society. So whether you're beginning to peel back the layers of this technological onion, or you're a seasoned tech aficionado keen on the latest trends, today's journey through the realms of machine learning and AI ethics ensures insights for everyone. Strap in, adjust your headphones, and prepare for launch. Our mission to demystify AI starts now. Imagine we're throwing together a grand feast where each dish represents a different aspect of machine learning and AI. It's like Hell's Kitchen, but with less yelling and more algorithms. We kick off with the appetizer supervised learning. Think of it as following a recipe from a celebrity chef's cookbook. You expect a Michelin star dish, but sometimes you end up with something only your dog would love. Nailed it. Next, we come up to the soup du jour, performance evaluation. I'll have that. Just like tasting soup, to make sure it doesn't taste like warm wallpaper paste, we check our AI models to ensure they're not just spitting out fancy gibberish. For our main course, we have the daring, unsupervised learning. It's like throwing together what's left in your fridge and hoping it doesn't start a new ecosystem. No recipes, just pure culinary chaos that somehow ends up delicious. Moving on to the meticulous art of data mastery, which is a bit like making sure your vegetables are washed and chopped. Nobody wants a side of E. coli with their data steak. Our side dish tonight involves backpropagation. Imagine trying to unburn your toast by tweaking the toaster settings. Sounds impossible, but that's kind of what we're doing here, learning from the burnt bits to make perfect toast next time. And for dessert, the sweet science of reinforcement learning. It's like baking a cake and letting your guests tell you what's missing. More sugar? Less flour, perhaps? By the end of the party, it's a masterpiece. Don't forget our cheese board of bias and privacy. Vital considerations to ensure everyone enjoys the meal without worrying about who's been double dipping in the data dip. We wrap up with a toast to building ethical AI. It's about cooking up technology that not only tastes good, but is also good for the soul, ensuring everyone leaves our table both full and happy. Join us as we mix, stir, and sometimes spill our way through the world of AI. Discover the art and science that makes up each course. Who knows? You might just find that understanding AI is as satisfying as one of your grandma's secret recipes. Let's start with some of the most dynamic methods in machine learning: neural networks and supervised learning. Like a skilled chef who expertly manages a variety of ingredients to perfect a dish, these techniques utilize diverse data elements to predict and analyze with great accuracy. Picture a city's road network as a complex web where intersections are neurons and roads are synapses. Each car, or data point, travels along these roads and is processed at intersections based on the rules of the road, or activation functions. The paths, we'll call them weights, adjust based on the traffic flow, input data, optimizing routes, outputs, to avoid congestion, errors. This urban landscape of data vividly illustrates the dynamic processing within neural networks, showing how connections are weighted and adjusted to streamline the flow of information. In our brain, each neuron acts like a tiny processor, making decisions based on the input it receives from others. Neural networks in AI work on a similar principle. When we feed data into the network, it travels along these roads, and at each stop are artificial neurons. Tiny calculations are made. These might be simple calculations, like adding up numbers, or more complex functions that decide which way the data should go next. Let's say we're teaching this network to recognize photos of animals. We input thousands of pictures, and each image is like a traveler navigating the city, going from neuron to neuron. Initially, these travelers are a bit lost. They bump into a lot of dead ends and take wrong turns. However, as more images pass through, the network learns from its mistakes, adjusting its paths and intersections, or weights and biases in tech speak. It's learning the best routes to take for cat pictures versus dog pictures, just like a seasoned taxi driver learns to avoid traffic jams during rush hour. Over time, these pathways become so efficient that the network can quickly and accurately identify what it sees, whether it's a cat, a dog, or a bear. Oh my. This ability to learn and improve over time makes neural networks incredibly powerful for tasks like image recognition, voice recognition, and even playing complex video games against human opponents. And the best part? Unlike human learners, these networks don't forget their lessons over summer break. They retain and refine their knowledge as long as they're used. So whether it's powering the Face ID on your phone or helping doctors diagnose diseases from medical images, neural networks are the magic behind countless AI applications that are becoming as commonplace as smartphones in our pockets. Having explored how neural networks can learn and adapt through complex data pathways, we now turn our attention to support vector machines. These models excel at creating precise boundaries between different data categories, providing a stark contrast to the continuous learning style of neural networks. Support vector machines, or SVMs, might sound like they belong in a sci-fi arsenal, but they are actually a powerful tool in machine learning. Let's explore this concept with a simple day at the beach scenario. For For those of you that know me, this is actually an unlikely occurrence. Think of a beach where shells and pebbles are scattered all over the sand. Your task is to use a large rake to create a boundary line in the sand that separates shells from pebbles as clearly as possible. You adjust this line based on the positions where you see shells and pebbles mixed up, trying to minimize these overlaps. This is what SVMs do in a computational landscape. They find the best boundary or hyperplane in a multidimensional space that divides different categories of data with maximum margin, reducing misclassifications. In machine learning, SVMs do exactly that. But instead of shells and pebbles, they're sorting data points. Think of each shell or pebble as a piece of data that needs to be classified. SVMs look for the best possible line, and by line, I mean boundary, that can divide these data points into groups. In 2 dimensions, this boundary is a line, but in 3, it becomes a plane, and in more complex data sets, we call it a hyperplane. For instance, if we're trying to distinguish between photos of cats and dogs, we'll leave bears out of it for a moment. The SVMs would analyze the characteristics of each photo. It determines the best boundary that separates cat characteristics from dog characteristics, ensuring that each animal falls on the correct side of the line. Now, back to our beach scenario, just as you might adjust your line as you see a shell or pebble out of place, SVMs adjust their boundaries based on the data. They push the line as far as possible from the nearest points of each group to minimize errors. This method is not only used for identifying animals in photos, but also plays a crucial role in voice recognition systems, handwriting analysis, and even financial models to detect potential fraud. So while it might not help with your beach activities, in the digital world, SVMs are invaluable for keeping things on the right side of the line, be it cats, checks, or characters. Now, let's shift gears to a method in machine learning as intuitive as it is practical: decision trees. Think of it as playing an elaborate game of 20 questions, except in this game, each question helps us make precise decisions, from identifying spam emails to deciding if you should bring an umbrella for those of us that go outside. Imagine you're trying to guess an object your friend is thinking of. You start by asking yes or no questions that rapidly split your possibilities, narrowing down your guesses based on the answers. Is it alive? Is it bigger than a bread box? And so on. In the world of AI, decision trees do something remarkably similar. They split data by asking a series of questions, each one dividing the data into smaller and smaller groups until they make a decision or classification. Each question forms a node in the tree, and the possible answers branch off into further questions or decisions. Let's apply this to something like sorting emails into spam or not spam. The tree might start with the question, does the email contain the word prince? If the answer is yes, the path might lead to a branch labeled likely spam. If no, the next question might be, does it have a company email address? And so forth. By the end of the game, or the tree, each leaf represents a final decision. It's a bit like navigating a maze. Each choice leads you closer to your final destination. And just like in the game of 20 questions, the skill lies in knowing what questions to ask and when. In machine learning, this means choosing the right features and thresholds to most effectively split your data. So whether you're trying to outsmart your spam filter or just beat your niece at a guessing game, thinking like a decision tree can give you the edge. Just remember, unlike your niece, the decision tree won't get tired of playing after too many questions. With decision trees, we can split data effectively to make informed decisions, but how do we measure the accuracy of these decisions? This leads us into our next crucial topic: performance metrics. Okay, let's pretend our machine learning models are contestants on a talent show, and we're the judges with scorecards. To rate their performances, we use some key metrics: accuracy, precision, recall, and the F1 score. It's not just about clapping for every trick. We need to be sure they're hitting the right notes. Think of accuracy as the overall percentage of times the contestant or our model gets the right answer, whether it's a hit or a miss. Now, precision is more about how many of our model's yes answers were actually correct. It's like judging a singer for pitch accuracy. Did they hit the perfect notes when they said they would? Recall, on the other hand, measures whether our model managed to catch all the yes cases. Using our talent show analogy, it's like checking if the singer remembered all the right lyrics. And then there's the F1 score, which balances precision and recall, a bit like having a judge who weighs both singing talent and stage presence. These metrics come into play in serious scenarios too, like medical diagnostics. Imagine using them to evaluate a test for a disease. Precision here would mean the test accurately identifies patients who actually have the disease without false alarms. High recall would mean the test correctly identifies all patients with the disease, ensuring no one is mistakenly given a clean bill of health. So next time you watch a talent show, you might just find yourself applying machine learning metrics to rate performers. I know I do. Just don't shout out, "That's a low recall rate," at the screen. People might look at you funny. I may know from experience. Understanding the effectiveness of our models through metrics like precision and recall is vital. Equally important is ensuring that our models are robust and reliable across various scenarios. Which brings us to the next concepts of training and testing. Imagine machine learning as studying for a big, unpredictable exam. Overfitting is like cramming all the answers the night before. It might help you on one specific test, but it won't actually teach you the material. What happens if the questions change? Suddenly, all that memorization is as useful as a chocolate teapot. Chocolate teapot. That sounds delicious. To combat this, we use a technique called cross-validation, which is akin to taking several mock exams before the big day. This method allows us to test our machine learning model on different sets of questions, ensuring it really understands the material and isn't just memorizing it. Cross-validation splits the data into multiple parts. We train our model on one part and test it on another, rotating which part is used for testing. It's like rotating the goalie in hockey to make sure everyone is game ready, no matter where the puck flies. Let's revisit one of our previous examples. Let's say we're training a model to predict whether emails are spam or not. With cross-validation, we check how well our model performs on different batches of emails, not just one set. This helps us ensure that our spam filters won't just work well for last week's junk mail, but also for whatever gets tossed our way next month. So while overfitting might get you through some situations, using cross-validation ensures our AI is ready for the real world, capable of handling new challenges on the fly without needing a cram session the night before. And let's be honest, nobody likes cramming for exams, not even computers. Okay, maybe computers. No, not even computers. All right, let's tackle k-means clustering next. If you've ever sorted your book collection or decided to organize your closet, you've got a head start in understanding this concept. It's like when you decide to group all your books by genre or all your clothes by color, even if you don't have labels on them. K-means clustering helps us find groups, or clusters, in a bunch of data without being told in advance what those groups should be. It's like having a pile of different sports balls and grouping them into types without knowing which are footballs and which are basketballs. The algorithm sorts them by similarity, all on its own. Imagine you throw a mixed bag of marbles onto the floor. Some are big, some are shiny, some are both. K-means clustering is like a robot vacuum that goes around and sucks up marbles that are all alike into a neat little group. It uses a mathematical formula instead of eyes to decide which marbles go where, but you get the idea. Technically, it works by picking a few central points at random. Think of them as the captains picking teams in gym class. Each data point, or marble, is then assigned to the nearest captain based on how similar it is to others around it. The centers keep moving and teams keep updating until the best grouping is achieved. In real life, businesses use this to understand customer behavior. Say a store wants to group customers by buying habits without knowing in advance any categories. They use K-means to automatically find these patterns. Maybe one group buys lots of baby clothes, another loads up on sports gear, and a third can't resist a sale on kitchen gadgets. It's the bow tie way, after all. So next time you see clusters of data points in a graph looking as organized as a well-kept bookshelf, you'll know that K-means clustering might just be the librarian behind the scenes, making sure every data point has found its proper place on the shelf. Now let's unravel the mysteries of hierarchical clustering. If K-means clustering is about grouping sports balls, hierarchical clustering is about building a family tree where each member is a data point. Imagine you're at a huge family reunion. Hierarchical clustering works like a curious guest wandering around, introducing people to one another based on how similar they look. Oh, you both have blue eyes. You might be second cousins. You both love gardening. Perhaps you're from the same branch of the family tree. This method doesn't just lump data together in one go. It builds relationships in a step-by-step manner, starting from each individual point and combining them into groups, then merging those groups into bigger ones, and so on. It's like organizing a picture album, starting with individual photos, then putting them into albums by event, and finally stacking those albums into boxes by year. Technically speaking, it calculates the distance or difference between data points and gradually links the closest ones together, creating a tree-like structure. Each link represents a relationship, and the length of the link shows how closely related the points are. In a real-world application, think of how you might categorize your music library. Hierarchical clustering could help sort your songs into genres and subgenres, then further into playlists that gradually group together similar tunes based on beats, lyrics, and artists. So next time you're trying to figure out your distant relations at the family gathering, remember that hierarchical clustering might just give you a clearer picture, just hopefully without all the awkward, so how are we related again? Conversations. All right. We've just navigated through the complex family trees of hierarchical clustering, finding out how everything from your favorite songs to distant relatives might be connected. Now, let's switch gears and explore another fascinating aspect of machine learning. Just like clustering helps us understand groupings, there are techniques that help us simplify and understand large, complex data sets. As we continue, we'll explore methods to simplify high-dimensional data while retaining its essential features. It's like moving from learning how to sort books to understanding how to create a concise summary of an entire library. Not only how we organize information, but how we make it more accessible and understandable. So to reiterate, clustering helps us understand the natural groupings within our data, providing insights into similarities and differences. However, dealing with very high-dimensional data can still be overwhelming. To address this, we turn to dimensionality reduction techniques like principal component analysis, PCA, and T-distributed stochastic neighboring embedding, or TSNE, which simplify the data while preserving its key aspects. Let's first talk about principal component analysis, or PCA. Imagine you have a huge cookbook full of recipes, thousands of them. Now, PCA is like creating a super condensed cheat sheet from that cookbook. This isn't just any cheat sheet, it's the kind that preserves all the essential flavors. So you still have all your key recipes at a glance without flipping through 1,000 pages. What PCA really does is it takes a massive amount of data and distills it down to the most important parts. It's like extracting the greatest hits of data points. This way, you can focus on what really matters without getting lost in the noise. Technically, PCA finds the directions of maximum variance in high dimensional data and projects it onto a new subspace with equal or fewer dimensions than the original one. If that sounds complex, think of it like reducing a detailed map into a simplified yet accurate sketch. From this sketch, you can still navigate and see the key features without the clutter, making it easier to understand the essential layout. Imagine your kitchen pantry is overflowing with spices, ingredients, and all sorts of cooking tools, many of which you rarely use. Dimensionality reduction is like organizing this chaos by creating a minimalist pantry that includes only those ingredients that you use most frequently and that contribute the most to your cooking. Just like focusing on essential flavors can improve a dish, this technique improves data analysis by reducing noise and complexity, making the essential data more accessible and manageable. And like that, PCA helps to reduce the clutter in your data, keeping only the most impactful flavors, so to speak. In real-world applications, like in image processing, PCA is used to reduce the number of pixels in images while keeping the picture almost as good as the original. It's like being able to recognize your favorite celebrity in a photo, even if it's a bit blurry. This makes the data easier to work with and analyze, especially when you're dealing with huge tracts of, data sets. Huge data sets. So PCA helps us by simplifying the complex, focusing on the essentials, and making our data analysis both efficient and effective. It ensures we aren't overwhelmed by data, but can still whip up pretty insightful conclusions. Kind of how, like, a good summary lets you ace a test without reading every single page of the textbook. Now, let's switch gears and talk about something called T-SNE, which stands for T-Distributed Stochastic Neighboring Embedding. Imagine you're at a huge dinner party with lots of guests. T-SNE is like the ultimate party planner who arranges the seating chart to ensure that everyone sits next to someone with similar interests. What T-SNE does is take a complex, multidimensional data set, or MDS, and reduces it down to 2 or 3 dimensions, which makes it much easier to visualize. It's like sorting a vast library of books into just a few shelves by topic so you can find what you're looking for at a glance. Think of it like your social media feed. Imagine if an algorithm could rearrange your feed so that posts about topics you care about most are always on top, while less relevant posts are pushed to the bottom. That's T-SNE. It groups similar data points together to make patterns easier to spot, just like clustering your favorite types of news together. It's kind of like being able to walk into a room and instantly see who's into vintage comic books, who's obsessed with reality TV, and who's a hardcore gamer. T-SNE helps data scientists quickly see who hangs out with whom in the data world, without having to manually check each person's profile. In real-world terms, T-SNE is used for things like customer segmentation, genetic clustering, or even detecting fraud patterns. It's powerful because it can handle the kind of data complexity that would give even the best dinner party planner a headache. So next time you see a beautifully organized chart or graph that seems to highlight all the right clusters of data, you can thank T-SNE for not only keeping the data party under control, but also making sure everyone is grouped by their favorite conversation topics. We're about to see how machines don't just categorize data, but also make complex decisions and adapt from their experiences, akin to navigating a bustling city market. We'll explore the significant ethical questions raised by these capabilities and what they mean for our future. First up, ethics in data collection. Because yes, even in the realm of data, there's a naughty or nice list. And let's face it, nobody wants their AI to end up being the bad guy. Ensuring ethical data collection is crucial because relying on flawed data is like building a house on sand. It might stand for a while, but eventually, it's going to collapse. Let me paint a picture for you with the tale of biased facial recognition technology. It's kind of like that one friend who never seems to remember names unless everyone is wearing a name tag. Now imagine if that friend was a security system that couldn't recognize your face just because you didn't fit the normal profile it was trained on. Not so funny anymore, right? But here's how we can avoid these ethical pitfalls. Think of it as making a salad. Yes, a data salad. First, anonymize personal information to protect identities. Then, toss your data to mix up diverse data sets. This ensures a rich, flavorful mix that promotes fairness and reduces biases. By doing so, our AI systems grow to be as open-minded as they are intelligent, not just repeating past mistakes, but learning to view the world through a more inclusive lens. Ethical data collection isn't just about avoiding bias. It's about actively creating systems that reflect the diverse world we live in. For instance, when collecting data for facial recognition, it's important to gather images from a wide array of ethnic backgrounds, ages, and other demographic factors. This diversity in data helps to train models that can accurately recognize and react to a broader spectrum of human features. Imagine you're a chef trying to make the perfect stew. You wouldn't use just one type of spice, right? Similarly, using a variety data set is like using a blend of spices to enhance the flavor of your dish. And just as a good chef tastes the stew throughout cooking, we must continuously test our AI models to ensure they perform well for everyone, not just a select few. So as we move forward into more technical waters, remember that the foundation of all effective and reliable AI begins right here, with the ethical collection and thoughtful preparation of data. This is what ensures our technological advancements are beneficial and fair, paving the way for AI that truly enhances human efforts across all walks of life. With our ethical bases covered, let's gear up to explore the nuts and bolts of how we actually prepare this data for use. Next on our tech menu is data cleaning, which, contrary to what it might sound like, involves zero soap and not a single drop of water. Instead, imagine you're set to cook a gourmet meal, let's say pasta. But instead of high quality spaghetti, half of your noodles are rubber bands. Not very appetizing or effective, right? That's what poorly cleaned data does to AI models. It messes them up before they even get the chance to start performing. The process of cleaning our data involves several crucial techniques. First up is filling in the blanks, known technically as imputation. It's like patching up holes in a melody so the music plays smoothly without any jarring interruptions. Then we normalize the data, which means adjusting everything to a common scale, akin to tuning all instruments in an orchestra to the same key, ensuring they play in harmony rather than in a chaotic cacophony. Let's break it down a bit more. Imputation might involve substituting missing or invalid entries with average values or median values, depending on what makes sense for the specific data at hand. This is crucial because missing data can lead to biased models that skew in one direction or another, much like a seesaw with weight only on one side. Normalization, on the other hand, often involves methods like min-max scaling or z-score standardization. Imagine you're measuring ingredients for a cake in both cups and milliliters, but your recipe only works if everything is measured in cups. Normalizing would convert all those milliliters into cups, ensuring that all data points contribute equally to the final outcome, preventing any one value from disproportionately influencing the model's performance. Think of data cleaning as preparing your kitchen before you start cooking. You wouldn't start with a dirty stove or a cluttered countertop, right? Similarly, AI needs a clean, well organized data set to work effectively. This step ensures that the AI doesn't end up making decisions based on erroneous or misleading information, like trying to bake a cake with salt, mistakenly labeled as sugar. So while it might not be the most glamorous part of machine learning, data cleaning is absolutely essential. It's the unsung hero that prevents our technological feast from turning into a disaster. Up next, we'll stir in some creativity and see how feature engineering can spice up our dataset, making it not just palatable, but truly delectable. Feature engineering is like deciding what ingredients to throw into our AI's cooking pot. It's a bit like picking the right spices for your stew. Miss one, and you might just turn a gourmet meal into a bland mush. For instance, if you're trying to predict how many ice creams will sell, knowing the temperatures outside can be more useful than the phases of the moon. We take raw data, like dates, and cook up useful features, like, is it a weekend? Because more ice cream gets sold on weekends, right? You might have noticed I've been using a lot of cooking analogies today. What can I say? What can I say? All this talk about data and models must be making me hungry. But I assure you, we're cooking up some serious knowledge here, not just lunch. Speaking of weather, let's stick with that theme. Imagine we're using weather data to predict umbrella sales. By selecting features like rainfall level and day of the week, we effectively teach our model to forecast when you'll most likely need to carry an umbrella. Think of it as teaching your model to peek out the window and check if it's raining before it reminds you to grab your umbrella. Practical, right? All right, we've just seasoned our understanding with a dash of data mastery, from ethical data gathering to the fine art of feature engineering. Now that we've prepped our kitchen, let's actually start cooking. So far, we've touched on supervised and unsupervised learning. Think of them as two different cooking techniques. In supervised learning, it's like following a recipe book with precise instructions. Add 2 cups of labeled data, stir in the right algorithm, and voila, you get a model that knows exactly what to do with new data. On the other hand, unsupervised learning is like being a freestyle chef. You're given ingredients, but no recipe. You mix and match, taste and adjust until you find patterns that taste just right. You create your own recipe based on the ingredients or data you have. We're going to dig deeper into these cooking learning styles. We'll see how these methods help machines turn raw data into delicious insights without needing a Michelin star. But first, apparently I need to take a break and eat something. My stomach thinks all this talk of food is for real. Alexa, what's the best snack for a podcast marathon? All right, back from that much needed snack break. Having explored how neural networks function like complex brain-like structures, we now turn to a fundamental technique that powers their learning: back propagation. This isn't just about minor tweaks, it's about systematically enhancing how our network processes information by learning from past mistakes. Let's unpack this essential process that sharpens neural accuracy and improves decision-making capabilities. Here's a straightforward way to see it. Each time a neural network errors, it learns to do better. Backpropagation is the method it uses to learn from these mistakes. Specifically, it adjusts the strengths or weights of the connections between neurons based on observed errors. These modifications help the network enhance its functionality over time, enabling it to perform tasks like understanding speech or navigating traffic more effectively. In backpropagation, incorrect outputs prompt the network to change its internal settings, specifically the weights that determine how neurons influence each other. By continually adjusting these weights based on errors, the network progressively improves. This ongoing refinement is crucial for evolving technologies such as voice recognition systems and autonomous vehicles. Ultimately, backpropagation encourages these systems to learn and adapt from their mistakes, creating a strong feedback loop. This continuous improvement cycle not only makes AI more effective, but also more intuitive. ensuring each interaction with technology gets better than the last. For instance, consider your smartphone's speech recognition feature. Initially, it might struggle to understand you in noisy environments. Each mistake it makes is used to fine tune the network through backpropagation, enhancing its ability to decode your speech more accurately with every attempt. Similarly, consider how Netflix optimizes its recommendations. It analyzes your viewing habits and continuously adjusts its algorithms via backpropagation. Each movie you watch and rate helps it refine its predictions, slowly getting better at suggesting shows you might enjoy. Backpropagation enables these technologies to learn from their errors. This process isn't just about correcting minor issues, it facilitates significant improvements. Every error is a chance for growth, helping these systems become more efficient and attuned to your preferences over time. Having seen how backpropagation fine-tunes our neural networks, let's now explore its vital role in the broader learning process. This mechanism isn't just correcting errors, it's optimizing the entire network. Like I said, backpropagation carefully adjusts the connections or weights between neurons to decrease errors, systematically improving the network's performance and efficiency. Imagine sculpting a statue from marble. Each stroke of the chisel doesn't just chip away excess material, it helps reveal the figure within. Each error in a neural network acts like a guide for backpropagation, signaling where to make these chisel strokes, adjustments to weight, to improve the network's output. Over time, like a sculptor perfecting their art, backpropagation refines the network to better perform its tasks. Similarly, think of a cyclist making incremental adjustments to their bike's setup based on race results. Small tweaks, like altering the seat height or changing gear ratios, akin to adjusting weights, are based on performance feedback, enhancing future rides. In the same way, backpropagation modifies the neural network based on feedback from past activities to optimize future outcomes. This process underpins improvements in technologies you use every day. For instance, voice assistants like Siri or Google Assistant become more accurate over time because backpropagation fine-tunes their ability to interpret your requests more precisely after each interaction. Similarly, the predictive text on your smartphone learns from your typing habits to better predict your next words. And you can ducking count on it. Complex applications, such as autonomous vehicles, also rely heavily on backpropagation. Each time a self-driving car encounters a new scenario, it uses data from that event to adjust its driving algorithms, making better informed decisions in the future. This continuous learning process ensures that the car's performance improves with each drive. Backpropagation is what makes modern AI dynamic and responsive, allowing systems to adapt and evolve based on new data, unlike older static models. It's this capability for ongoing learning and adaptation that sets apart sophisticated AI systems and drives their success in real-world applications. Ultimately, the ability to learn from and adapt to mistakes through backpropagation is a fundamental aspect of AI's problem-solving prowess. It ensures that AI systems are not just repeating programmed tasks, but are continuously evolving and improving based on real-world experiences. Backpropagation isn't just a technical concept. It has a rich history that transformed artificial intelligence. First conceptualized in the 1970s, it became a cornerstone technique in the 1980s thanks to pioneers like Geoffrey Hinton. This method helped neural networks learn from their mistakes, drastically improving their abilities. The adoption of backpropagation marked the beginning of what many experts call the second wave of AI. It revolutionized how machines processed information, enabling them to perform complex tasks like intricate decision-making that were once thought impossible for computers. As we look forward, the potential for backpropagation continues to expand. With advances in computational power and more complex neural network designs, we are on the brink of seeing AI accomplish tasks once relegated to the realm of science fiction, like creating art or formulating new scientific theories. Imagine a world where AI systems equipped with sophisticated backpropagation algorithms could predict economic trends or innovate new materials. These systems might one day not just analyze vast data sets, but also think creatively to solve problems no human has tackled before. Backpropagation is key to these advancements because it constantly refines and improves neural networks. Think of it as a feedback loop in engineering. Each cycle sharpens the AI's functions, enhancing its accuracy and broadening its capabilities. As this technology evolves, it promises to reshape our interaction with machines. AI systems are becoming more intuitive and adaptable, learning in ways that mirror human cognition. The journey of AI, powered by backpropagation, is one of relentless improvement and endless possibility. This continuous cycle of learning and adapting makes backpropagation not just a tool for enhancing AI, but a transformative force in technology. It's paving the way for AI systems that are not only more reliable, but also more integrated into our daily lives, capable of supporting complex, creative problem solving. But with great power comes great, well, again, you get it. Backpropagation significantly boosts AI's learning capabilities, but it also raises complex ethical challenges. A major concern is its potential to unintentionally reinforce existing biases in the data it learns from. Imagine an AI system trained continuously on historical data that includes biases. These could be racial, gender, or socioeconomic biases. Backpropagation might not only replicate but also intensify these biases, embedding them deeper into the AI's decisions. This makes it imperative to use data that is as clean and unbiased as possible. Another critical issue is the black box nature of AI systems using backpropagation. This refers to the opacity of the decision-making processes in these systems, making it hard for even their creators to track how decisions are made. Addressing these ethical challenges requires a collective effort from all stakeholders in AI, including engineers, ethicists, and policymakers. It's about building AI responsibly to ensure it aligns with societal values and does not perpetuate harmful biases. We need to cultivate a culture of transparency and accountability in AI development. Implementing strict ethical guidelines and conducting thorough audits are crucial steps in mitigating risks and promoting fairness. Our creations today will shape our future. We must steer AI development towards outcomes that reflect our shared ethical standards, ensuring that these powerful technologies enhance societal well-being. Let's remain diligent as we advance AI's capabilities. By fostering open discussions about AI's ethical aspects and participating in policymaking, we can help structure a future where AI supports all aspects of human dignity. Exploring backpropagation has shown us not only its technical significance, but also its broader impact on AI and society. It highlights the crucial role we all play as both creators and consumers of these technologies. Backpropagation embodies the principles of learning and adaptation, essential for both AI and human development. Each adjustment in a network teaches us about the power of learning from mistakes, offering a potent metaphor for personal and professional growth. As we explore more advanced AI technologies, we carry forward this theme of continual improvement, crucial for driving technological and personal advancement. Now, we turn our attention to reinforcement learning, where AI systems learn from direct experience. This method teaches machines to make strategic decisions, enhancing their ability to act intelligently in varied situations, paralleling how we learn from our own life experiences. Moving on from our exploration of neural network learning mechanisms, we now enter the exciting and dynamic world of reinforcement learning, or RL. Think of it as the difference between studying from a book and learning through life's practical experiences. In RL, machines learn from the consequences of their actions, akin to how video game characters evolve by navigating challenges, not merely aiming for high scores, but learning to strategize and optimize their decisions over time. Here, AI systems effectively earn points for making smart, well judged moves, enhancing their capability to handle complex, real world tasks. Imagine if every time you made a choice, there was a little cheer or boo from an invisible crowd, guiding you on what you do next. That's RL in a nutshell. Through trial and error and a lot of virtual cheers and boos, these algorithms learn to navigate complex environments and make decisions that maximize their rewards. Now let's imagine you're training a dog, not by giving direct commands, but by using a system of rewards and sounds. Each time the dog performs a task, it receives either a positive sound, like a click, or a treat for a correct action, or a different sound for an incorrect one. Over time, the dog learns to associate these sounds and rewards with specific behaviors. This method mirrors reinforcement learning, where algorithms learn optimal actions based on feedback from their environment, continuously improving their decision making skills. Over time, Fido learns what he needs to do to earn his treats. In the tech world, RL algorithms learn from the outcomes of their actions, figuring out over time which actions bring the biggest treats or rewards based on the goals we've set for them. This type of learning isn't just about performing well under known conditions, it's about adapting to new challenges and optimizing behavior. From optimizing your route home based on traffic conditions to winning at chess or Go against world champions, RL algorithms are pushing the boundaries of what machines can learn on their own. And it's not all fun and games. The principles of RL are used in very practical scenarios too, like developing smarter navigation systems that learn the best routes over time or managing investment portfolios to maximize returns without the investor having to micromanage every decision. But as cool as all this sounds, it raises a lot of questions. How do we ensure these systems make ethical decisions if they're just chasing the metaphorical carrot? What happens when the best decisions for the algorithm isn't the best decision for humans involved? This segues perfectly into our next topic, ethics in AI, where we'll tackle these tough questions head on. But before we get into the moral maze, let's ponder this. If an AI gets really good at maximizing its rewards, could it potentially learn behavior we didn't intend? Keep that in mind as we explore the ethical landscape these technologies navigate. Hold on to your headphones because things are about to get even more interesting. All right, let's unravel the mystery of bias in AI. Just like that one friend who always thinks the movie is going to end badly, biases in AI can taint its decisions, leading to some wonky outcomes. Imagine a set of scales that always tips slightly to one side. A small error might not just mess up your recipe, but could lead to significant inaccuracies. Bias comes in many flavors. Data bias could happen if the info feeding the algorithm is like a fruit bowl that's all apples and no oranges, leading to a pretty one sided diet. Then there's algorithmic bias, which occurs if the recipe, the code, favors one outcome over another, akin to a cookbook that suggests using way too much salt in every dish. There I go with those food references again. We might as well run with it. So, how do we fix a biased AI? Well, it's a bit like making sure your fruit bowl has a good mix of fruits. Ensuring our data is diverse helps the AI avoid developing a sweet tooth for any particular flavor. It's all about balance, which keeps our AI systems healthy and fair. For example, Diverse training data and continuous testing are like cross training for your AI. Just as athletes train across different disciplines to improve their overall fitness, we cross train our AI with different kinds of data and situations to help it perform well across the board. Imagine an AI trained to detect spam messages, but it's only ever seen examples from one part of the world. It might start marking all emails with the word sale as spam. Hilarious, but not very helpful. It's like mistaking every orange for a basketball. Just because they're both round doesn't mean they belong in the same category. And that's why we keep our data varied and our code checked. We don't want an AI that thinks every circular object is for throwing. That could lead to some unexpected sports in the office. As we venture further into the digital age, the topic of privacy becomes increasingly intricate and vital. Picture the General Data Protection Regulation, or GDPR, as Europe's heavyweight champion in the privacy arena. Much like a vigilant headmaster, it ensures that companies play fair with your personal data, enforcing rules that protect your privacy across the continent. And it's not just a European concern. Across the pond in California, the California Consumer Privacy Act, or CCPA, serves as a local sheriff in the Wild West of the internet. This law arms citizens with the right to guard their digital presence, ensuring personal data isn't just another commodity to be traded. Zooming out to a global scale, we see a myriad of privacy laws shaping how data is handled from Australia to Brazil, each adding a layer of protection like knights guarding a castle. These laws collectively work towards a common goal: to ensure that your personal information, from your shopping habits to online chats, doesn't fall into the wrong hands without your consent. Although, why would we ever consent to our data falling into the wrong hands? I don't know. Now, let's introduce a game changer in the privacy playbook: privacy enhancing computation, or PEC. Imagine it as a secret agent for your data. This tech allows companies to decrypt insights from your information without ever actually seeing it. Picture a magician who performs a mind-blowing trick blindfolded without ever touching the hat or the rabbit. PEC operates by encrypting data in such a way that it remains concealed even during analysis. It's like having an invisible cloak over your personal information. Businesses can use it to make informed decisions, but they can't peek underneath the cloak. This means they can predict your preferences and needs without ever accessing your data directly. With technologies like PEC coming to the forefront, we're not just looking at basic compliance with laws, but a revolution in how privacy is integrated into every aspect of digital interaction. This isn't just about avoiding penalties, it's about redefining trust in the digital age. Now let's dive into a concept straight out of a cyber thriller: adversarial machine learning. Picture this. It's like convincing Sherlock Holmes that Moriarty is the hero and he's the villain. These crafty manipulations coax AI systems into making errors by feeding them misleading data, a digital sleight of hand that could lead to all sorts of mayhem. Contending with these threats is akin to an epic chess match played on a global scale, a cerebral battle of attrition between cybersecurity knights and hacking marauders. Each move is calculated to outsmart and outplay the opponent, using a mix of cunning strategies and bold gambits. It's a high-stakes game where the prize is nothing less than our digital safety and security. In adversarial machine learning, attackers might alter an image just slightly, tweaking it in ways that are imperceptible to humans, but lead AI like self-driving cars or facial recognition systems to misinterpret what they see. It's as though someone painted a mustache on Mona Lisa's face, and suddenly she's mistaken for Salvador Dali by an AI trained to know better. This digital battleground is where our privacy policies like GDPR and cybersecurity measures are tested daily. It's about more than just keeping our data safe, it's about maintaining the integrity of our digital personas against a backdrop of increasingly sophisticated threats. As we forge ahead, we must stay vigilant, ensuring our digital fortress is both strong and fair, guarding against the dragons of data misuse and the specters of cyber sabotage. And speaking of safeguarding our digital realms, if you're as intrigued by these battles in the byte field as I am, keep your ears peeled for a bonus episode coming soon. We'll go further into the world of cybersecurity, pulling back the curtain on how these digital defenders keep us safe. It's a topic close to my heart, given my background, and I can't wait to share more insights and stories with you. But as we wrap up today's exploration of AI's ethical and security challenges, remember, this isn't just about protecting data. It's about upholding our rights and freedoms in the digital age. We're not only combating data breaches and intrusive surveillance, but also championing personal liberty and integrity. As we near the end of our journey today, let's pivot to a critical aspect of AI that affects not just how it's built, but why and for whom. We're talking about building ethical AI that's inclusive, sustainable, and regulated with the best interests of all in mind. Imagine entering a building that only had stairs, no ramps, no elevators. That's a world without inclusive design. Now, think about AI in the same context. We aim to create technology that everyone can use, regardless of their physical abilities or where they come from. It's like making sure there are ramps in every digital park and pathways that everyone can tread. Why is this important? Well, imagine an AI that only learns from one type of voice or one cultural perspective. It would be a pretty narrow view of the world, right? We strive to prevent that by integrating a kaleidoscope of human experiences into our datasets and by designing interfaces that cater to all, whether it's someone using a screen reader or someone who communicates in sign language. So how do we craft such universally accessible AI? First, we use datasets as diverse as the global population, representing various ages, ethnicities, abilities, and more. This ensures our AI learns from a rich tapestry of human conditions. Secondly, we design user interfaces that are intuitive for everyone. Consider voice recognition systems that can understand a myriad of accents, or text-to-speech that is clear no matter your hearing ability. For instance, by ensuring that an AI used in healthcare can understand medical queries in multiple languages, or making sure a virtual reality setup has options for users with motion sensitivity, we're not just building technology, we're building technology that brings people together rather than segregating them. As we marvel at AI's capabilities, it's also crucial to talk about its footprint. Yes, even digital wizards have a carbon footprint. Training some of the most advanced AI models can consume as much energy as entire cities do in a year. It's a bit like a supercar, impressive performance, but boy, does it guzzle fuel. Now, imagine this scenario. Every time we teach an AI new tricks, it's like sending a rocket into space. The energy required is astronomical. We need to ensure that our journey into AI development is not leaving a trail of ecological debt. So what's being done about this? Companies like Google are leading by example, powering their behemoth data centers with renewable energy, wind, solar, you name it. It's akin to retrofitting an old muscle car to run on clean energy, not just cutting down emissions, but paving the way for a greener future. And what can we do? Just as we might choose a hybrid or electric vehicle to reduce our carbon footprint, we can develop AI algorithms that are not only smart, but also energy efficient. By optimizing how these AIs learn, think of it as tuning your car for better gas mileage, we can help mitigate their environmental impact. It's about creating AI that not only thinks fast, but also thinks green. By adopting strategies like using greener data centers and designing more efficient models, we're not just innovating, we're ensuring that our digital progress doesn't cost the earth, literally. As we navigate through the realm of AI, it's essential to have some ground rules. Think of the EU's ethics guidelines for trustworthy AI as the rulebook for the digital age. These aren't just any rules, they're designed to ensure that AI behaves in a manner that is fair, transparent, and accountable, much like a referee in a sports game, making sure all plays are fair. Go sports ball. But creating these guidelines is just the beginning. Across the globe, from the shores of California with its Consumer Privacy Act to the bustling markets of Asia, efforts are underway to develop regulations that keep up with the swift pace of AI innovation. These laws are like the evolving rules of the road as new, faster vehicles, RAIs, come into play, aiming to balance innovation with safety and privacy. And guess what? It's not just the big tech firms or governments rolling up their sleeves. It's a team effort. Everyone from the developer in Silicon Valley to the casual smartphone user in Nairobi has a role in shaping these policies. It's like a global town hall where every voice contributes to how we build a trustworthy digital future. That's why your opinion matters. These policies impact how your data is used, how safe your digital interactions are, and even how the next generation of AI technologies will evolve. It's about crafting a tech ecosystem that respects our values and reflects our diversity, ensuring AI advances with humanity's best interests at heart. So, as we look into the future, let's continue this dialogue, keep asking tough questions, and actively participate in the regulatory landscape. By staying informed and engaged, we can help steer the development of AI in a direction that safeguards our rights and enriches our lives. Let's ground these ideas with some real-world implications. Imagine AI being used in a hiring process. Without proper guidelines, this AI could inadvertently favor certain groups over others based on biased data. This is where strong ethical standards come into play, guiding AI to aid rather than hinder fair employment practices. Here's a scenario for you. An AI system is tasked with screening job applicants, but it has been trained mostly on data from male candidates. This could skew its decision-making unfairly against other humans. It's cases like these that ethical frameworks aim to prevent by ensuring AI systems are trained on diverse datasets. Think about this. How would you feel if you knew your job application was evaluated by an AI that hadn't been properly checked for bias? Pretty unsettling, right? That's why discussions about regulations are so crucial. They help us to ensure that AI is used in a way that's fair and just for everyone. These aren't just hypotheticals. They're real issues that have happened and can happen again if we're not careful. By advocating for and adhering to stringent ethical guidelines, we can harness AI's potential while minimizing its risk. So let's all be vigilant and push for policies that hold AI to the highest ethical standards. Your voice matters in this debate. Together, we can shape an AI-powered future that holds the values we believe in. Well, that wraps up our whirlwind tour through the ever-twisting corridors of machine learning and AI ethics. It's been like trying to solve a Rubik's Cube that rearranges itself every time you blink. Always a wild ride with new surprises at every turn. Rotation. Today we've untangled some complex webs and considered how we, as a community, play a pivotal role in weaving the ethical tapestry that will shape the future of AI. Our journey through the nuances of neural networks and the moral mazes of machine ethics has been both revealing and inspiring. Now it's your turn to jump into the fray. Did today's exploration open new perspectives for you, or did it reinforce your existing views? Whatever your insights, they enrich our collective understanding. Join the discussion on our website at humanguide2.ai or connect with us on social media using the handle @humanguide2ai. Whether you're sharing ideas, questions, or even AI-driven doodles, your contributions make this journey even more rewarding. Thank you for tuning in to AI Explored, the Human's Guide to the Future. I'm Jeremy, unquestionably human and perpetually fascinated by our digital counterparts. Until we decode more mysteries together, stay curious, keep dreaming expansively, and never cease to explore. Remember, the future isn't pre written, it's crafted by our collective imagination, one episode at a time.